Hi, my name is Shreya Jairam, and this is my video for Physics 2212 Experiment 4, Faraday's Law. Introduction. The purpose of this lab is to simulate Faraday's Law by using the data from dropping a magnet into an aluminum tube. The fundamental principles used were Faraday's Law, the Biot-Savart Law, Newton's second law, Ohm's law, magnetic force on a loop, and the time derivative of magnetic flux induced by a dipole. The final results of this lab were that the experimental time for the magnet to leave the tube was 1.604 seconds, and the computational time was 1.647 seconds. So the models were Faraday's Law, which says that EMF is equal to negative n, which is the number of loops, times the derivative of, so delta phi over delta t. And the Biot-Savart law says that B is equal to mu naught times Ni over 2R. Newton's second law says that F is equal to Ma. Ohm's law says I is equal to V over R. Magnetic force on a loop says that force is equal to I 2 pi R times B of the magnet times sine theta. And the time derivative of the magnetic flux says that d phi dt is equal to 3 mu naught times mu m times distance times speed times r squared over 2 times r squared plus d squared to the power of 5 over 2. So in the experiment, the length of the tube was 0.31 meters, the width was 0.01 meters, inner radius was 0.015 meters, the total radius was 0.025 meters, the mu that I had from lab 2 was 2.59, the mass of the magnet was 0.023 kilograms, the average time that I calculated was 1.604 seconds. Our assumptions were that air resistance is negligible and magnetic force and gravitational force are the only forces acting on the system. The system was the earth, tube, and magnet, and the surroundings was everything else. So in our code, I have the values listed before from the experiment here, and then this was the function to determine the dipole of the magnet. This was the function to determine the flux of the magnet, and then this was to determine F net, which just says that F net is equal to the magnetic force plus the gravitational force. And then here we have Newton's law to update the velocity and position of the magnet. And here we have two graphs. So this first graph was using my mu value of 2.59, which I got from lab 2, which gave me a time of about 4.6 seconds. However, my experimental time was less than that, so when I changed around the mu value, I found that a mu value of 1.55 gave me the closest time to my experimental value, which was in this case 1.647 seconds. So discussion. When looking from above, the red ring corresponds to counterclockwise current, while the blue ring corresponds to clockwise current. This is because the red end represents the north end where the magnetic field is coming up from the magnet, and the blue end represents the south end where the magnetic field is going into the magnet. As mentioned before, the time in the tube given by the computational model at first using the mu calculated in lab 2 gave a time of 4.573 seconds, while my experimental time was only 1.604 seconds. This is most likely due to calculating mu inaccurately in lab 2, so upon changing the mu value to 1.55, I was able to get a time of 1.647, which is closer to my experimental time. And the shape of the velocity versus time graph tells me that there's no magnetic force immediately after dropping the magnet into the tube and immediately after it exits. Since there's only gravitational force acting down, the velocity points downwards in those moments. So in checkpoint 1 from the lab, the question was asked if we could use a Ferris tube for this experiment, and my answer was that we cannot use a Ferris tube because the magnetic field of the iron in the tube would interfere with the field of the bar magnet, causing the magnet to stick to the side of the tube rather than falling through. And in checkpoint 2, my answer was the magnet falling through the tube takes much more time to fall than it would if it was in free fall without a tube. So for the first what-if question, I said if the resistivity of the conductor was reduced to closer to 0, it would greatly increase the time the magnet took to pass through the tube, as the induced current would be much higher due to Ohm's law. And for the second what-if question, I said if holes or slots were cut into the tube, the current would be decreased since there would not be as many complete rings in the tube, so the time the magnet took to fall would decrease. In conclusion, I was able to model Faraday's law to gain a better understanding of how the law works in a practical application. I used various fundamental principles such as the Biot-Savart law and the Ohm's law to help me develop a computational model, and this experiment deepened my understanding of induced current and magnetic flux. Thank you.